Hey everybody, welcome back. Today we're going to talk a little bit about something related to the effective stress of soil, and that's capillarity and partial soil saturation. Now this is something that most engineers will typically ignore in order to be conservative, and because it's easier to ignore it. But having a fundamental understanding of what really is going on in the soil can be helpful in understanding behavior that you might observe in the field. Now, here's a typical profile that one might sketch of soil at a site. And we have different zones here in the soil. For instance, we have a zone that might be dry or nearly dry up near the ground surface where the soil is desiccated. And then as we move deeper down in the soil, we begin to see more saturation, more water, and so it becomes partially saturated. And deeper down still, we eventually will get to where the soil is saturated. But what's interesting is we're still not below the water table. That's right. The soil can be saturated above the water table. And so we can be still in the zone of capillary rise. And then, of course, if we go beneath the water table, we'd like to think that we're saturated. That's a common assumption. In nature, it's actually quite common to be unsaturated beneath the water table if you're in an area that has a lot of organics or a lot of frequent groundwater changes or groundwater level fluctuations with the seasons. But the point here that we're trying to make is that in the area of partial saturation and even saturation in the zone of capillary rise, we're going to have negative pore pressures. So let's liken this scenario to sticking a tube into a fluid. Now when we stick this tube into the fluid is going to rise up into the tube using capillary action. Now let's go ahead and study what's going to happen at three different points within this scenario here. And we're going to study it using good old Bernoulli's equation, or the energy equation, modified slightly. We removed the velocity head because we're dealing with fluid flow through soil, so velocities are very, very small. So we're going to assume velocity head is equal to 0. So here we go. I've got 3 points. Let's look at point A first of all. So point A is right here. It's on the surface of the fluid. Here is my datum. It's equal to the height of the top of the fluid. Because elevation head, h sub z, is equal to the vertical distance from my datum to my point of interest. And because my point of interest is right on top of my datum, then I would say that the elevation head for point A is equal to 0. Also, because the point is right on the surface of the fluid, exposed to atmosphere, it's experiencing 0 pressure from the fluid. So I would say that my pressure head at point A is equal to 0 as well. And since total head is the summation of elevation head and pressure head, then all I have to do is add those together, and to get my total head, I get 0. Now here's something that's interesting. I have point B right here. Okay, point B. Now point B is equal or is at the elevation of the water surface, but it's inside my capillary tube. So my elevation head it's still right on top of the datum, so that means that elevation head is equal to 0. But interestingly enough, the pressure head right there is also equal to 0. And we've seen this effect before when we've dealt with capillarity, and we talked about it in my 341 class, that if I can measure pore pressure inside of that capillary tube, the pore pressure would be negative. And if I could go down into the fluid, beneath the capillary tube, the pressure would be positive. But right at the elevation of the surface of the fluid, the pressure is always equal to 0. So that means that the pore pressure, or the pressure head, is also equal to 0. So that means that the total head is equal to 0. Now, if I look at point C at the top of the fluid, My elevation head is obviously above the datum, and it's above the datum a distance of h sub c. Okay, well that means then that my elevation head is not equal to 0. But what is my pressure head? Well, my pressure head is going to simply equal the height up into the capillary tube that I've gone. And so it's equal to pore pressure, which would be negative U divided by gamma W. And that's going to just simply give me the height of H sub C. But negative, because it's going to be negative pore pressure. See how that is a negative there instead of a positive when I go up into the capillary tube? So my pressure head is equal to negative H sub C. So if I add those two together, I still have a net sum energy of 0. And that's the point that we're trying to take here, is that whenever we're dealing with water or fluid inside the capillary tube, or fluid right at the surface of our water here, or of the container of the fluid, we're always dealing with 0 net energy. And just because we have fluid up in here in this tube doesn't mean that we magically created energy out of thin air. All of the fluid in this tube still has to have a net energy of 0. All we're doing is manipulating now the pressure and the elevation head in order to do that. So if we take a closer look at the forces that are going on inside that capillary tube, and we do a free body diagram, we can see really that there's two forces going on. We have a force that's lifting the water up into the tube, and then we have the weight of the fluid that's trying to pull itself down in the tube. Now, the force that's lifting the fluid up into the tube, that T, that's going to equal the surface tension of the fluid, which physicists have measured to be very, very small, and roughly 0.072 to 0.075 newtons per meter. And we have to account for the suspension or the angle of that tension. It's not vertical or horizontal. It does suspend at an angle known as the wetting angle. So that's where that cosine alpha comes from. And then that tension is being distributed across a diaphragm, or across a circumference of the tube there. So that's where that gamma D comes from, where D is the diameter of our tube. Now, this equation right here is the weight of the fluid inside the tube, and that's simply equal to the cross-sectional area of our tube times the height of the fluid in the tube times its unit weight, and that gives us the weight of the fluid in the tube. Since we know that the sum of the forces in the vertical direction must equal 0 in order to maintain static equilibrium, we can set the weight of the fluid equal to the tensile uplift of the fluid, and we can then create our governing equation in this manner. And then we can solve for any parameter that we want to. In this instance, we're going to solve for the height of capillary rise inside the tube. And this is the equation that we derive. So this equation will tell us how high into this tube, this fluid or this water will rise inside this capillary tube. Now, this equation also applies to soil, but we have to come up with an equivalent diameter of the soil porosity in order to use it. Now, some researchers back in the 1940s, Lane and Washburn, they performed an experiment on some soil in a tube. It was cohesionless soil, in other words, a sand, and they did two samples. In one sample, they put fully saturated sand in the tube, and they submerged the bottom of the tube into a tub of water like this. In the second sample, sample B, they placed fully dry sand in the tube, and then they placed that dry sand tube, submerged the bottom of it into a similar tub of water in such manner. And then what they did was they measured the degree of saturation in the tubes with the distance above the phreatic line. And what we get are two different lines from these two experiments. Line A corresponds to the curve they measured when they did the experiment on fully saturated sand. Now, in this instance, the sand initiated saturated, but began to drain when they stuck it into the tube of water. Thus, we call it the drainage curve. So that represents line A here, okay? Now, the second line, line B, this represents the curve they measured when they placed the completely dry soil into the water, and they call it the wetting curve. So this is the curve that they measured when the soil is initially dry. Now, some other dimensions that they labeled, HCX, this is called the maximum capillary head. HCS, right there, is called the saturation capillary head. Now, notice that we have 100 degrees saturation for the drainage curve. HCR, right here, this is the peak of the wetting curve. This represents capillary rise, and it's the minimum height that capillary rise will occur in the soil. And then HCN right here, this represents the minimum capillary head, and it represents the zone of the minimum height of constant saturation in the soil. But notice that it's not equal to 100% degree of saturation, and that's because the soils started initially dry. So these two curves, in essence, represent boundaries of what we would expect for the two extreme conditions of soil, fully saturated or fully non-saturated, or in other words, fully dry. And every condition of the soil is going to fall between these two boundaries. So these boundaries, in essence, represent bookends. They represent the two extremes experienced by the soil. And the actual degree of saturation at any time is going to be somewhere between these two lines. Why is the drainage and the wetting behavior different between these two curves? Well, in the case of the saturated soil, the soil in the void, or the moisture in the voids, provides a lattice for the capillary action to climb higher. The fluid rising from the water has an easier time climbing with the water than it does just climbing on the soil particles themselves. And so it will produce that zone of capillary rise to a higher extent than it does in the fully dry soil. So this is what we're facing. We understand as engineers that the soil is going to look something like this, where we have a dry to moist zone, a totally saturated zone, but still above the water table, and then saturation below the water table. So if we were to plot degree of saturation with depth, it would look something like this. The problem is we have no clue what those actual numbers are, and we have no clue where the soil actually reaches 100% degree of saturation. If we did, we would be able to predict with certainty the extent of where the pore pressure changes, or how high it'll go up negative, and where it changes from negative to positive. We would have absolute certainty on that. But the problem is, once we lose 100% degree of saturation, we don't know what the pore pressure is in that soil. It varies and it changes. It's very, very dynamic. We can predict with pretty good accuracy the total stress that the soil is feeling. And if we knew with certainty what the pore pressure was, we could compute with certainty what the effective stress in the soil was. So, down to the zone of capillary rise, we are good. And beneath the water table, down in this zone, where we can compute hydrostatic pore pressures, we are also good. The problem, and where we have the freak show occurring, is right in here, where we know negative pore pressures exist, but we don't really have a way to predict them. And it's in this zone that we don't really know what we're doing. So what do we typically do? If we want to account, and that's a big if, by the way, if engineers want to account for the zone of capillary rise, they're going to assume some zone of total saturation above the water table. And they're going to assume then that the water rises, or that there's negative pore pressures that are equal to negative unit weight of water times the height that water is rising above the water table, right? Right up until we assume that the water, or that the soil is no longer 100% saturated, and at which point we assume zero pore pressure. And so if we then plot that with our total stress and subtract pore pressure from our total stress, we end up again with this zone right here, where instead of having, the effective stress like we wanted to show it, we get an increase in effective stress due to the negative pore pressures in the zone of capillary rise. So that's typically how we account for it. And why do we do it this way as engineers? Well, for one, we know that this stuff up here, the zone of partial saturation, and I'll call it the ZPS. The ZPS is constantly changing. We can't really rely on it. This zone of saturation doesn't change that much. It's pretty constant. But the zone of partial saturation is changing all the time. And even if we could predict where that zone was with accuracy, we have no idea what the pore pressure behavior is inside that zone. It's very, very complex. So we're just going to assume zero pore pressure within that zone. That's constantly or commonly what engineers are doing in practice today. So if we have negative pore pressures in the zone of capillary rise, what is that doing to our effective stress of the soil? Well, remember, effective stress equals total stress minus pore pressure. If I have negative pore pressure, that's just going to increase my effective stress. So that's going to cause an increase in my interparticle stress. In other words, my effective stress is going to essentially and effectively increase. But in practical terms, what does this mean? And how does the soil going to behave? Well, it's going to appear like the soil has more strength or an apparent cohesion in it. In other words, the soil will have a stickiness to it, or it'll feel stiffer for some reason. And folks, this is why if you ever go to the beach and you want to build a sandcastle, you have to make the sand moist, because it's that moisture between the sand particles, the tension between of the water between the sand particles that is holding the sand particles together and giving it apparent strength. Otherwise, the sand would just fall apart and fall to the ground. So that's essentially what this negative pore pressure looks like in soil. So there's a couple of real-life examples we can consider. For instance, so I went to school, I studied with a professor by the name of Robert Holtz. He was teaching at the time at the University of Washington, and he's kind of a legend in the geotechnical community, and I enjoyed greatly the classes that I had for Professor Holtz. In his books, Introduction to Geotechnical Engineering by Holtz and Kovacs, he talks about an example of the racetrack at Daytona Beach, Florida. And, he gave this figure in the track where he says, here's the water, and obviously driving a car down by the water, the sand is too loose, and the wheels are going to rut in the sand, and it's not good to drive on. And if you get up too far away from the water, the sand gets dry, and you have the same effect. If you try to drive in it, your wheels get stuck easily in the sand, and the sand ruts, and it's just not good for driving. But there is a sweet spot. There's a zone just above the water, but below the dry sand, where you have really good soil, good bearing capacity. You can drive on it, and you'd have all these races. And I remember Professor Holtz talking about this, and I would just scratch my head because I was like, what are you talking about? Racetrack at Daytona Beach, Florida. Well, it's because I found out that they used to have races there. And so here's some pictures that I found from the web. The very first NASCAR races in the United States were literally held on Daytona Beach, on the sand. And this is a picture back from the 1950s. So in the 1940s and the 1950s, they were racing right on the beach, okay? And you can see some of these pictures of them racing. Now, there's one picture here I really want to look at. Yeah, this one right here. I don't think my pen works on the browser. But if you look at this picture, you can see that the sand is a little bit darker right where the cars are driving. It's not saturated. It's not totally wet. Otherwise, the cars are driving in the ocean. But the sand is just moist. And that's the perfect consistency, that perfect negative pore pressure to give some apparent cohesion to that sand to allow those cars to race on it. The reason I had no idea what Professor Holtz was talking about was that in 1958, they built the Daytona 500 Speedway, and they don't race on the beach anymore. But I thought that was kind of funny that he still uses that example, and none of us students had any clue what he was talking about. Another example that you could do yourself if you ever wanted to do an experiment, you can go get a balloon or a rubber glove, anything like that, and you can fill it part way up with sand and then suck all of the air as much as you can out of that balloon, and while it's still under that vacuum, close the balloon off, twist it, and tie a knot in it so that you trap that vacuum in with that sand. And you're going to feel that if you do it correctly, that the sand inside that balloon or that rubber glove is going to be, it's going to feel almost like clay. You'll be able to mold it, shape it, and form shapes out of it, which is maybe counterintuitive because we expect to be able to do that in soil like clay that we know is plastic and moldable. It's kind of neat to see us be able to do that with a soil like sand. So here's some text right out of the Holtz and Kovacs text, or the Holtz and Kovacs book. And it talks a little bit about, if you get coarse-grained soils like sands or granular soils, if you get them moist, they will have some apparent strength. And if you make a vertical cut in them, they will retain that vertical cut shape as long as the soil is moist and that water tension can hold those particles together. But as soon as that soil dries out, you lose the bonding between those soil particles and the sand becomes just like dry sand. I've seen construction operations where they've tried to rely upon this moist sand to make vertical cuts. And if the weather is really warm or they leave those cuts exposed to the atmosphere for long enough and the soil dries out, I've seen instances where excavations have collapsed, buried equipment, buried people, killed people. It's a big deal. And you don't need the soil to dry out. You can also have instances where you just have vibrations from like construction equipment can cause the tension from the water to break and can cause failures as well. And so if you're involved in construction or construction methods, this is something you need to be aware of. And every time you choose to make an open cut or a vertical cut in moist granular soil, you're gambling essentially, because that soil is not able to sustain a steep or a vertical cut on its own unless it's moist. So what about that partially saturated soil? What do we do about it? Well, and how do we compute the effective stress in it? So it's a common assumption that the air does not contribute to pore pressure, but in truth, it really does. You know, air is a fluid just like water is. And so air does contribute pressure to the soil particles and does impact effective stress. So in 1959, a famous engineer named Bishop, he derived a basic relationship for computing vertical effective stress in partially saturated soils using this equation right here, where the effective stress in partial saturated soils is essentially equal to the effective stress, and it's equal to the total stress minus the pore pressure due to the air in the voids, plus this factor from the pore pressure due to the fluids or the water in the voids, okay? And that is equal to this X times the pore pressure from the air minus the pore pressure from the water. Now, X, he said, would be equal to 1 if the soil was completely saturated. So if you plug in 1 for X, you see that the UAs cancel out, and all I'm left with is total stress minus pore pressure from the water. That's the equation that you've always used for effective stress. And if the soil is completely dry, that X is equal to 0, which means then that all we have to account for is the pore pressure from the air. In reality, it's going to be some number between 0 and 1 if the soil is moist. And that's the rub, right? Is what is it? Something between 0 and 1. So a lot of different researchers have really looked at this and studied it. And they've tried to measure what that value of X is. And the tricky thing is that it's soil specific. I could take 2 different types of clays and they will give me 2 completely different curves. So what these curves demonstrate, by the way, is the degree of saturation of the soil versus the measured value of X, okay? And you can see, for instance, for this particular test, we get some curve that looks like that. For different soils, like a glacial moraine, we got, this curve. For a boulder clay, the researchers Blight 1961 got that curve. For a different boulder clay, same soil, different location, it produced a different curve. And for a clay shell, it produced a curve that looked like this, okay? And so we're kind of all over the map. But what a lot of researchers have noticed is, what if we just assume a linear relationship where we assume that X is just equal to the degree of saturation? So in other words, if my degree of saturation is 20%, then X equals 0.2. My degree of saturation is 40%, then X is equal to 0.4. So on and so forth. And we see that if we assume that type of relationship, it's a pretty good approximation of the general shape of the soils, of all soils. Yeah, sure, individual soils will be above or below that line, but we're pretty close if we just follow that general assumption. So a lot of engineers began to use that simplified equation to estimate X. That X is simply equal to the degree of saturation in decimal form. So if we plug that simplifying assumption into Bishop's equation, we end up with this equation that I talked about in my 341 course for effective stress in the zone of capillary rise, or anywhere where we have partially saturated soils. So in other words, effective stress is just equal to this relationship right here, where it's total stress minus pore pressure, where pore pressure is the degree of saturation times negative unit weight of water times the height above the water table. And in that instance, if we're in the zone of capillary rise, effective stresses are going to be larger than total stresses because pore pressures are going to be negative, and we're subtracting a negative number. So famous geotechnical engineers, wonderful textbook, Lamb and Whitman, they have an interesting example in there where they show some measurements of stresses that they did in a fine uniform sand with varying degree of saturation. And they show how the degree of saturation varies with depth in millimeters here, or centimeters, excuse me, from the top of the soil sample. So you can see it starts somewhere around 37%, increases slightly with depth, and once they get down to this depth down here below about 50 centimeters or 40 centimeters above the water, it became 100% degree of saturation. Okay? So the plots here on the right represent different ways to plot stress with the elevation in the soil. So if we just wanted to plot the total stress, it's just simply the unit weight of the soil times the depth in the soil. So we get this line right here. So that line that I tried to highlight is the total stress. Now, if we just assume that the degree of saturation is 1 all the way up where there's moisture content and then goes straight to 0 from that point on, then we would get this curve right here where we'd say, all right, let's assume that the degree of saturation is going to be equal to 1, so the pore pressure in that zone is simply going to equal negative gamma water times height. And you can see if that's the case that we get some really crazy high effective stresses, the higher above the water table we go. And then the second we get up into this zone where we assume 0 saturation, we get an immediate jump at this point all the way down to 0 stress, which doesn't really make sense. If you're confused by this plot right here that I'm highlighting, there's good reason, because it's bogus and it doesn't exist. And so that plot isn't real and it doesn't make sense. But instead, if we assume this relationship right here, where we account for the degree of saturation and we compute our pore pressures that way, we end up with a curve that looks something like this. And guess what? That's the curve that closely represented reality based on Lamb and Whitman's testing. And so we think that's a pretty good method for approximating effective stresses within the zone of partially saturated soil. If this is a topic that interests you, then I strongly recommend you to check out the textbook by Friedland and Raharjo called Soil Mechanics for Unsaturated Soils. It's a very good reference and will fit nicely on your geotechnical engineering bookshelf. So until next time, stay dirty, my friends, and I will catch you for the next lesson when we will talk about stresses and invariance in soils. Thank you.